A microprocessor incorporates the functions of a computer's central processing unit on a single integrated circuit, or at most a few integrated circuits. All modern CPUs are microprocessors, making the micro prefix redundant. The microprocessor is a multipurpose, programmable device that accepts digital data as input, processes it according to instructions stored in its memory, and provides results as output. It is an example of sequential digital logic, as it has internal memory. Microprocessors operate on numbers and symbols represented in the binary numeral system. The integration of a whole CPU onto a single chip or on a few chips greatly reduced the cost of processing power. The integrated circuit processor was produced in large numbers by highly automated processes, so unit cost was low. Single-chip processors increase reliability as there are many fewer electrical connections to fail. As microprocessor designs get faster, the cost of manufacturing a chip generally stays the same. Before microprocessors, small computers had been implemented using racks of circuit boards with many medium and small-scale integrated circuits. Microprocessors integrated this into one or a few large-scale ICs. Continued increases in microprocessor capacity have since rendered other forms of computers almost completely obsolete, with one or more microprocessors used in everything from the smallest embedded systems and handheld devices to the largest mainframes and supercomputers. Structure. The internal arrangement of a microprocessor varies depending on the age of the design and the intended purposes of the processor. The complexity of an integrated circuit is bounded by physical limitations of the number of transistors that can be put onto one chip, the number of package terminations that can connect the processor to other parts of the system, the number of interconnections it is possible to make on the chip, and the heat that the chip can dissipate. Advancing technology makes more complex and powerful chips feasible to manufacture. A minimal hypothetical microprocessor might only include an arithmetic logic unit and a control logic section. The ALU performs operations such as addition, subtraction, and operations such as AND or OR. Each operation of the ALU sets one or more flags in a status register, which indicate the results of the last operation. The logic section retrieves instruction operation codes from memory, and initiates whatever sequence of operations of the ALU requires to carry out the instruction. A single operation code might affect many individual data paths, registers, and other elements of the processor. As integrated circuit technology advanced, it was feasible to manufacture more and more complex processors on a single chip. The size of data objects became larger. Allowing more transistors on a chip allowed word sizes to increase from 4 and 8-bit words up to today's 64-bit words. Additional features were added to the processor architecture. More on-chip registers sped up programs, and complex instructions could be used to make more compact programs. Floating-point arithmetic, for example, was often not available on 8-bit microprocessors, but had to be carried out in software. Integration of the floating-point unit first as a separate integrated circuit and then as part of the same microprocessor chip, sped up floating-point calculations. Occasionally, physical limitations of integrated circuits made such practices as a bit-slice approach necessary. Instead of processing all of a long word on one integrated circuit, multiple circuits in parallel processed subsets of each data word. While this required extra logic to handle, for example, carry and overflow within each slice, the result was a system that could handle, say, 32-bit words using integrated circuits with a capacity for only 4 bits each. With the ability to put large numbers of transistors on one chip, it becomes feasible to integrate memory on the same die as the processor. This CPU cache has the advantage of faster access than off-chip memory, and increases the processing speed of the system for many applications. Processor clock frequency has increased more rapidly than external memory speed, except in the recent past, so cache memory is necessary if the processor is not delayed by slower external memory. Special purpose designs. A microprocessor is a general-purpose system. Several specialized processing devices are followed from the technology. Microcontrollers integrate a microprocessor with peripheral devices in embedded systems. A digital signal processor is specialized for signal processing. Graphics processing units may have no, limited, or general programming facilities. For example, GPUs through the 1990s were mostly non-programmable and have only recently gained limited facilities like programmable vertex shaders. 32-bit processors have more digital logic than narrower processors, so 32-bit processors produce more digital noise and have higher static consumption than narrower processors. So 8-bit or 16-bit processors are better than 32-bit processors for system-on-a-chip and microcontrollers that require extremely low-power electronics, or are part of a mixed-signal integrated circuit with noise-sensitive on-chip analog electronics such as high-resolution analog-to-digital converters, or both. When manufactured on a similar process, 8-bit micros use less power when operating and less power when sleeping than 32-bit micros. However, some people say a 32-bit micro may use less average power than an 8-bit micro, when the application requires certain operations, such as floating-point math, that take many more clock cycles on an 8-bit micro than a 32-bit micro, and so the 8-bit micro spends more time in high-power operating mode. Embedded applications. Thousands of items that were traditionally not computer-related include microprocessors. These include large and small household appliances, cars, car keys, tools and test instruments, toys, light switches, dimmers and electrical circuit breakers, smoke alarms, battery packs, and hi-fi audio-visual components. Such products as cellular telephones, DVD video system and HD TV broadcast systems fundamentally require consumer devices with powerful, low-cost, microprocessors. Increasingly stringent pollution control standards effectively require automobile manufacturers to use microprocessor engine management systems, to allow optimal control of emissions over widely varying operating conditions of an automobile. Non-programmable controls would require complex, bulky, or costly implementation to achieve the results possible with a microprocessor. A microprocessor control program can be easily tailored to different needs of a product line, allowing upgrades in performance with minimal redesign of the product. Different features can be implemented in different models of a product line at negligible production cost. Microprocessor control of a system can provide control strategies that would be impractical to implement using electromechanical controls or purpose-built electronic controls. For example, an engine control system in an automobile can adjust ignition timing based on engine speed, load on the engine, ambient temperature, and any observed tendency for knocking, allowing an automobile to operate on a range of fuel grades. History. The advent of low-cost computers on integrated circuits has transformed modern society. General-purpose microprocessors in personal computers are used for computation, text editing, multimedia display, and communication over the Internet. Many more microprocessors are part of embedded systems, providing digital control over myriad objects from appliances to automobiles to cellular phones and industrial process control. The first use of the term microprocessor is attributed to Viatran Computer Systems describing the custom integrated circuit used in their System 21 small computer system announced in 1968. Intel introduced its first 4-bit microprocessor 4004 in 1971 and its 8-bit microprocessor 8008 in 1972. During the 1960s, computer processors were constructed out of small and medium-scale ICs each containing from tens of transistors to a few hundred. These were placed and soldered onto printed circuit boards, and often multiple boards were interconnected in a chassis. The large number of discrete logic gates used more electrical power and therefore produced more heat than a more integrated design with fewer ICs. The distance that signals had to travel between ICs on the boards limited a computer's operating speed. In the NASA Apollo space missions to the Moon in the 1960s and 1970s, on-board computations for primary guidance, navigation and control were provided by a small custom processor called the Apollo Guidance Computer. It used wire-wrap circuit boards whose only logic elements were 3-input NOR gates. The first microprocessors emerged in the early 1970s and were used for electronic calculators, using binary-coded decimal arithmetic on 4-bit words. Other embedded uses of 4-bit and 8-bit microprocessors, such as terminals, printers, various kinds of automation etc., followed soon after. Affordable 8-bit microprocessors with 16-bit addressing also led to the first general-purpose microcomputers from the mid-1970s on. Since the early 1970s, the increase in capacity of microprocessors has followed Moore's law. This originally suggested that the number of components that can be fitted onto a chip doubles every year. With present technology, it is actually every 2 years, and as such Moore later changed the period to 2 years. Firsts, 3 projects delivered a microprocessor at about the same time: Garrett I Research's Central Air Data Computer, Texas Instruments TMS 1000, and Intel's 4004. CADC. In 1968, Garrett I Research was invited to produce a digital computer to compete with electromechanical systems then under development for the main flight control computer in the U.S. Navy's new F-14 Tomcat fighter. The design was complete by 1970, and used a MOS-based chipset as the core CPU. The design was significantly smaller and much more reliable than the mechanical systems it competed against, and was used in all of the early Tomcat models. This system contained a 20-bit, pipelined, parallel multi-microprocessor. The Navy refused to allow publication of the design until 1997. For this reason the CADC, and the MP944 chipset it used, are fairly unknown. Ray Holt graduated California Polytechnic University in 1968, and began his computer design career with the CADC. From its inception, it was shrouded in secrecy until 1998 when at Holt's request, the U.S. Navy allowed the documents into the public domain. Since then people have debated whether this was the first microprocessor. Holt has stated that no one has compared this microprocessor with those that came later. According to Parabay al., the scientific papers and literature published around 1971 reveal that the MP944 digital processor used for the F-14 Tomcat aircraft of the U.S. Navy qualifies as the first microprocessor. Although interesting, it was not a single-chip processor, as was not the Intel 4004. They both were more like a set of parallel building blocks you could use to make a general-purpose form. It contains a CPU, RAM, ROM, and 2 other support chips like the Intel 4004. It was made from the same P-channel technology, operated at military specifications and had larger chips, an excellent computer engineering design by any standards. Its design indicates a major advance over Intel, and 2 years earlier. It actually worked and was flying in the F-14 when the Intel 4004 was announced. It indicates that today our unregistered trademark industry theme of converging DSP microcontroller architectures was started in 1971. This convergence of DSP in microcontroller architectures is known as a digital signal controller. Gilbert Hyatt was awarded a patent claiming an invention predating both TI and Intel, describing a microcontroller. The patent was later invalidated, but not before substantial royalties were paid out. TMS 1000, the Smithsonian Institution says TI engineers Gary Boone and Michael Cochran succeeded in creating the first microcontroller and the first single-chip CPU in 1971. The result of their work was the TMS 1000, which went commercial in 1974. TI stressed the 4-bit TMS 1000 for use in pre-programmed embedded applications, introducing a version called the TMS 1802NC on September 17, 1971 that implemented a calculator on a chip. TI filed for a patent on the microprocessor. Gary Boone was awarded U.S. Patent 3,757,306 for the single-chip microprocessor architecture on September 4, 1973. In 1971 and again in 1976, Intel and TI entered into broad patent cross-licensing agreements, with Intel paying royalties to TI for the microprocessor patent. A history of these events is contained in court documentation from a legal dispute between Cyrix and Intel, with TI as intervener and owner of the microprocessor patent. A computer on a chip combines the microprocessor core, memory, and I/O lines onto one chip. The computer on a chip patent, called the microcomputer patent at the time, U.S. Patent 4,074,351, was awarded to Gary Boone and Michael J. Cochran of TI. Aside from this patent, the standard meaning of microcomputer is a computer using one or more microprocessors as its CPU, while the concept defined in the patent is more akin to a microcontroller. Intel 4004. The Intel 4004 is generally regarded as the first commercially available microprocessor, and cost $60. The first known advertisement for the 4004 is dated November 15, 1971 and appeared in Electronic News. The project that produced the 4004 originated in 1969, when Bizicom, a Japanese calculator manufacturer, asked Intel to build a chipset for high-performance desktop calculators. Bizicom's original design called for a programmable chipset consisting of 7 different chips. 3 of the chips were to make a special-purpose CPU with its programs stored in ROM and its data stored in shift register read-write memory. Ted Hoff, the Intel engineer assigned to evaluate the project, believed the Bizicom design could be simplified by using dynamic RAM storage for data, rather than shift register memory, and a more traditional general-purpose CPU architecture. Hoff came up with a Euro chip architectural proposal, a ROM chip for storing the programs, a dynamic RAM chip for storing data, a simple I/O device and a 4-bit central processing unit. Although not a chip designer, he felt the CPU could be integrated into a single chip, but as he lacked the technical know-how, the idea remained just a wish for the time being. While the architecture and specifications of the MCS4 came from the interaction of Hoff with Stanley Miza, a software engineer reporting to him, and with Bizicom engineer Masatoshi Shima, during 1969, Miza and Hoff moved on to other projects. In April 1970, Intel hired Italian-born engineer Federico Fagan as project leader, a move that ultimately made the single-chip CPU final design a reality. Fagan, who originally developed the silicon gate technology in 1968 at Fairchild Semiconductor and designed the world a unregistered trademark's first commercial integrated circuit using SGT, the Fairchild 3708, had the correct background to lead the project into what would become the first commercial general-purpose microprocessor. Since SGT was his very own invention, it, in addition to his new methodology for random logic design, made it possible to implement a single-chip CPU with the proper speed, power dissipation and cost. The manager of Intel's MOS design department was Leslie Alveda SZ at the time of the MCS4 development, but Vedas's attention was completely focused on the mainstream business of semiconductor memories, and he left the leadership and the management of the MCS4 project to Fagan, who was ultimately responsible for leading the 4004 project to its realization. Production units of the 4004 were first delivered to Bizicom in March 1971 and shipped to other customers in late 1971. Piko General Instrument. In 1971, Piko Electronics and General Instrument introduced their first collaboration in ICs, a complete single-chip calculator IC for the Monroe-Litton Royal Digital 3 calculator. This chip could also arguably lay claim to be one of the first microprocessors or microcontrollers having ROM, RAM and a RISC instruction set on chip. The layout for the 4 layers of the PMOS process was hand-drawn at X500 scale on mylar film, a significant task at the time given the complexity of the chip. Piko was spun out by 5 GI design engineers whose vision was to create single-chip calculator ICs. They had significant previous design experience on multiple calculator chipsets with both GI and Marconi Elliott. The key team members had originally been tasked by Elliott Automation to create an 8-bit computer in MOS and had helped establish a MOS research laboratory in Glenrothes, Scotland in 1967. Calculators were becoming the largest single market for semiconductors, and Piko and GI went on to have significant success in this burgeoning market. GI continued to innovate in microprocessors and microcontrollers with products including the CP1600, IOB 1680 and PIC 1650. In 1987, the GI microelectronics business was spun out into the microchip PIC microcontroller business. 4-phase systems AL1, The four-phase system's AL1 was an 8-bit bit slice chip containing 8 registers and an ALU. It was designed by Lee Boycell in 1969. At the time, it formed part of a 9-chip, 24-bit CPU with 3 AL1s, but it was later called a microprocessor when, in response to 1990s litigation by Texas Instruments, a demonstration system was constructed where a single AL1 formed part of a courtroom demonstration computer system, together with RAM, ROM, and an input-output device. 8-bit designs. The Intel 4004 was followed in 1972 by the Intel 8008, the world's first 8-bit microprocessor. The 8008 was not, however, an extension of the 4004 design, but instead the culmination of a separate design project at Intel, arising from a contract with Computer Terminals Corporation, of San Antonio, Texas, for a chip for a terminal they were designing. The data point 2200 Euro fundamental aspects of the design came not from Intel but from CTC. In 1968, CTC's Vic Poor and Harry Pyle developed the original design for the instruction set and operation of the processor. In 1969, CTC contracted 2 companies, Intel and Texas Instruments, to make a single-chip implementation, known as the CTC 1201. In late 1970 or early 1971, TI dropped out being unable to make a reliable part. In 1970, with Intel yet to deliver the part, CTC opted to use their own implementation in the data point 2200, using traditional TTL logic instead. Intel's version of the 1201 microprocessor arrived in late 1971, but was too late, slow, and required a number of additional support chips. CTC had no interest in using it. CTC had originally contracted Intel for the chip, and would have owed them $50,000 for their design work. To avoid paying for a chip they did not want, CTC released Intel from their contract and allowed them free use of the design. Intel marketed it as the 8008 in April 1972, as the world's first 8-bit microprocessor. It was the basis for the famous Mark 8 computer kit advertised in the magazine Radio Electronics in 1974. The 8008 was the precursor to the very successful Intel 8080, which offered much improved performance over the 8008 and required fewer support chips, Zilog Z80, and derivative Intel 8-bit processors. The competing Motorola 6800 was released August 1974 and the similar MOS technology 6502 in 1975. The 6502 family rivaled the Z80 in popularity during the 1980s. A low overall cost, small packaging, simple computer bus requirements, and sometimes the integration of extra circuitry allowed the home computer revolution to accelerate sharply in the early 1980s. This delivered such inexpensive machines as the Sinclair ZX81, which sold for $99. A variation of the 6502, the MOS technology 6510 was used in the Commodore 64 and yet another variant, the 8502, powered the Commodore 128. The Western Design Center, Incorporated introduced the CMOS 65C02 in 1982 and licensed the design to several firms. It was used as the CPU in the Apple II and ERIC personal computers as well as in medical implantable-grade pacemakers and defibrillators, automotive, industrial and consumer devices. WDC pioneered the licensing of microprocessor designs, later followed by ARM and other microprocessor intellectual property providers in the 1990s. Motorola introduced the MC6809 in 1978, an ambitious and well-thought-through 8-bit design which was source-compatible with the 6800 and was implemented using purely hardwired logic. Another early 8-bit microprocessor was the Signetics 2650, which enjoyed a brief surge of interest due to its innovative and powerful instruction set architecture. A seminal microprocessor in the world of spaceflight was RCA's RCA-1802, which was used on board the Galileo probe to Jupiter. RCA Cosmark was the first to implement CMOS technology. The CDP-1802 was used because it could be run at very low power, and because a variant was available fabricated using a special production process, silicon on sapphire, which provided much better protection against cosmic radiation and electrostatic discharge than that of any other processor of the era. Thus, the SOS version of the 1802 was said to be the first radiation-hardened microprocessor. The RCA 1802 had what is called a static design, meaning that the clock frequency could be made arbitrarily low, even to 0 Hz, a total stop condition. This let the Galileo spacecraft use minimum electric power for long uneventful stretches of a voyage. Timers or sensors would awaken the processor in time for important tasks, such as navigation updates, attitude control, data acquisition, and radio communication. Current versions of the Western Design Center 65C02 and 65C816 have static cores, and thus retain data even when the clock is completely halted. 12-bit designs, the Intersal 6100 family consisted of a 12-bit microprocessor and a range of peripheral support and memory ICs. The microprocessor recognized the DECP-DP8 mini-computer instruction set. As such, it was sometimes referred to as the CMOS-DP8. Since it was also produced by Harris Corporation, it was also known as the Harris HM6100. By virtue of its CMOS technology and associated benefits, the 6100 was being incorporated into some military designs until the early 1980s. 16-bit designs, the first multi-chip 16-bit microprocessor was the National Semiconductor IMP16, introduced in early 1973. An 8-bit version of the chipset was introduced in 1974 as the IMP8. Other early multi-chip 16-bit microprocessors include one that Digital Equipment Corporation used in the LSI-11 OEM board set and the packaged PDP-11/03 mini-computer Euro, and the Fairchild Semiconductor Microflame 9440, both introduced in 1975 Euro 1976. In 1975, National introduced the first 16-bit single-chip microprocessor, the National Semiconductor PACE, which was later followed by an NMOS version, the INS 8900. Another early single-chip 16-bit microprocessor was TI's TMS 9900, which was also compatible with their TI 990 line of mini-computers. The 9900 was used in the TI 990/4 mini-computer, the TI 99/4 home computer, and the TM990 line of OEM microcomputer boards. The chip was packaged in a large ceramic 64-pin DIP package, while most 8-bit microprocessors such as the Intel 8080 used the more common, smaller, and less expensive plastic 40-pin DIP. A follow-on chip, the TMS 9980, was designed to compete with the Intel 8080, had the full TI 990 16-bit instruction set, used a plastic 40-pin package, moved data 8 bits at a time, but could only address 16 KB. A third chip, the TMS 9995, was a new design. The family later expanded to include the 99105 and 99110. The Western Design Center introduced the CMOS 65816 16-bit upgrade of the WDC CMOS 65C02 in 1984. The 65816 16-bit microprocessor was the core of the Apple IIGS and later the Super Nintendo Entertainment System, making it one of the most popular 16-bit designs of all time. Intel upsized their 8080 design into the 16-bit Intel 8086, the first member of the x86 family, which powers most modern PC-type computers. Intel introduced the 8086 as a cost-effective way of porting software from the 8080 lines, and succeeded in winning much business on that premise. The 8088, a version of the 8086 that used an 8-bit external data bus, was the microprocessor in the first IBM PC. Intel then released the 80186 and 80188, the 80286 and, in 1985, the 32-bit 80386, cementing their PC market dominance with the processor family's backwards compatibility. The 80186 and 80188 were essentially versions of the 8086 and 8088, enhanced with some board peripherals and a few new instructions. They were not used in IBM-compatible PCs because the built-in peripherals and their locations in the memory map were incompatible with the IBM design. The 8086 and successors had an innovative but limited method of memory segmentation, while the 80286 introduced a full-featured segmented memory management unit. The 80386 introduced a flat 32-bit memory model with paged memory management. The Intel x86 processors up to and including the 80386 do not include floating-point units. Intel introduced the 8087, 80287, and 80387 math coprocessors to add hardware floating-point and transcendental function capabilities to the 8086 through 80386 CPUs. The 8087 works with the 8086/8088 and 80186/80188. The 80187 works with the 80186/80188. The 80287 works with the 80286 and 80386, and the 80387 works with the 80386. The combination of an x86 CPU and an x87 coprocessor forms a single multi-chip microprocessor. The two chips are programmed as a unit using a single integrated instruction set. Though the 8087 coprocessor is interfaced to the CPU through I/O ports in the CPU's address space, this is transparent to the program, which does not need to know about or access these I/O ports directly. The program accesses the coprocessor and its registers through normal instruction opcodes. Starting with the successor to the 80386, the 80486, the FPU was integrated with the control unit, MMU, and integer ALU in a pipeline design on a single chip, or the FPU was eliminated entirely. An ostensible coprocessor for the 80486SX, the 80487 was actually a complete 80486DX that disabled and replaced the coprocessorless 80486SX that it was installed to upgrade. 32-bit designs. 16-bit designs had only been on the market briefly when 32-bit implementations started to appear. The most significant of the 32-bit designs is the Motorola MC68000, introduced in 1979. The 68K, as it was widely known, had 32-bit registers in its programming model but used 16-bit internal data paths, 3 16-bit arithmetic logic units, and a 16-bit external data bus, and externally supported only 24-bit addresses. In PC-based IBM-compatible mainframes, the MC68000 internal microcode was modified to emulate the 32-bit System/370 IBM mainframe. Motorola generally described it as a 16-bit processor, though it clearly has 32-bit capable architecture. The combination of high performance, large memory space and fairly low cost made it the most popular CPU design of its class. The Apple Lisa and Macintosh designs made use of the 68000, as did a host of other designs in the mid-1980s, including the Atari ST and Commodore Amiga. The world's first single-chip fully 32-bit microprocessor, with 32-bit data paths, 32-bit buses, and 32-bit addresses, was the AT&T Bell Labs Bellmac 32A, with first samples in 1980, and general production in 1982. After the divestiture of AT&T in 1984, it was renamed the WE32000, and had two follow-on generations, the WE32100 and WE32200. These microprocessors were used in the AT&T 3B5 and 3B15 mini-computers. In the 3B2, the world's first desktop supermicrocomputer. In the Companion, the world's first 32-bit laptop computer. And in Alexander, the world's first book-sized supermicrocomputer, featuring ROM-pack memory cartridges similar to today's gaming consoles. All these systems ran the Unix System V operating system. The first commercial, single-chip, fully 32-bit microprocessor available on the market was the HP Focus. Intel's first 32-bit microprocessor was the IAPX 432, which was introduced in 1981 but was not a commercial success. It had an advanced capability-based object-oriented architecture, but poor performance compared to contemporary architectures such as Intel's own 80286, which was almost 4 times as fast on typical benchmark tests. However, the result for the IAP X432 was partly due to a rushed and therefore suboptimal Ada compiler. Motorola's success with the 68000 led to the MC68010, which added virtual memory support. The MC68020, introduced in 1984, added full 32-bit data and address buses. The 68020 became hugely popular in the Unix supermicrocomputer market, and many small companies produced desktop-size systems. The MC68030 was introduced next, improving upon the previous design by integrating the MMU into the chip. The continued success led to the MC68040, which included an FPU for better math performance. A 68050 failed to achieve its performance goals and was not released, and the follow-up MC68060 was released into a market saturated by much faster RISC designs. The 68K family faded from the desktop in the early 1990s. Other large companies designed the 68020 and follow-ons into embedded equipment. At one point, there were more 68020s in embedded equipment than there were Intel Pentiums in PCs. The cold-fire processor cores are derivatives of the venerable 68020. During this time, National Semiconductor introduced a very similar 16-bit pinout, 32-bit internal microprocessor called the Nova Scotia 16032, the full 32-bit version named the Nova Scotia 32032. Later, National Semiconductor produced the Nova Scotia 32132, which allowed 2 CPUs to reside on the same memory bus with built-in arbitration. The Nova Scotia 32016/32 outperformed the MC68000/10, but the Nova Scotia 32332 which arrived at approximately the same time as the MC68020 did not have enough performance. The third-generation chip, the Nova Scotia 32532, was different. It had about double the performance of the MC68030, which was released around the same time. The appearance of RISC processors like the AM29000 and MC88000 influenced the architecture of the final core, the Nova Scotia 32764. Technically advanced Euro with a superscalar RISC core, 64-bit bus, and internally overclocked Euro, it could still execute Series 32000 instructions through real-time translation. When National Semiconductor decided to leave the Unix market, the chip was redesigned into the Swordfish embedded processor with a set of on-chip peripherals. The chip turned out to be too expensive for the laser printer market and was killed. The design team went to Intel and they designed the Pentium Processor, which is very similar to the Nova Scotia 32764 core internally. The big success of the Series 32000 was in the laser printer market, where the NS32CG16 with microcoded bit BLT instructions had very good price performance and was adopted by large companies like Canon. By the mid-1980s, Sequent introduced the first SMP server-class computer using the Nova Scotia 32032. This was one of the design's few wins, and it disappeared in the late 1980s. The MIPS 2000 and A3000 were highly successful 32-bit RISC microprocessors. They were used in high-end workstations and servers by SGI, among others. Other designs included the Zilog Z80000, which arrived too late to market to stand a chance and disappeared quickly. The ARM first appeared in 1985. This is a RISC processor design, which has since come to dominate the 32-bit embedded systems processor space due in large part to its power efficiency, its licensing model, and its wide selection of system development tools. Semiconductor manufacturers generally license cores and integrate them into their own system-on-a-chip products. Only a few such vendors are licensed to modify the ARM cores. Most cell phones include an ARM processor, as do a wide variety of other products. There are microcontroller-oriented ARM cores without virtual memory support, as well as symmetric multiprocessor applications processors with virtual memory. In the late 1980s, microprocessor wars started killing off some of the microprocessors. Apparently, with only one bigger design win, Sequent, the Nova Scotia 32032 just faded out of existence, and Sequent switched to Intel microprocessors. From 1993 to 2003, the 32-bit x86 architectures became increasingly dominant in desktop, laptop, and server markets, and these microprocessors became faster and more capable. Intel had licensed early versions of the architecture to other companies, but declined to license the Pentium, so AMD and Cyrix built later versions of the architecture based on their own designs. During this span, these processors increased in complexity and capability by at least 3 orders of magnitude. Intel's Pentium line is probably the most famous and recognizable 32-bit processor model, at least with the public at broad. 64-bit designs in personal computers. While 64-bit microprocessor designs have been in use in several markets since the early 1990s, the early 2000s saw the introduction of 64-bit microprocessors targeted at the PC market. With AMD's introduction of a 64-bit architecture backwards compatible with x86, x86-64, in September 2003, followed by Intel's near-fully compatible 64-bit extensions, the 64-bit desktop era began. Both versions can run 32-bit legacy applications without any performance penalty as well as new 64-bit software. With operating systems Windows XP x64, Windows Vista x64, Windows 7 x64, Linux, BSD, and Mac OS X that run 64-bit native, the software is also geared to fully utilize the capabilities of such processors. The move to 64 bits is more than just an increase in register size from the IA32 as it also doubles the number of general-purpose registers. The move to 64 bits by PowerPC processors had been intended since the processor's design in the early 90s and was not a major cause of incompatibility. Existing integer registers are extended as are all related data pathways, but, as was the case with IA32, both floating point and vector units had been operating at or above 64 bits for several years. Unlike what happened when IA32 was extended to x86-64, no new general-purpose registers were added in 64-bit PowerPC, so any performance gained when using the 64-bit mode for applications making no use of the larger address space is minimal. In 2011, ARM introduced a new 64-bit ARM architecture, now used in iPhone 5s. Multi-core designs. A different approach to improving a computer's performance is to add extra processors, as in symmetric multiprocessing designs, which have been popular in servers and workstations since the early 1990s. Keeping up with Moore's law is becoming increasingly challenging as chip-making technologies approach their physical limits. In response, microprocessor manufacturers look for other ways to improve performance so they can maintain the momentum of constant upgrades. A multi-core processor is simply a single chip that contains more than one microprocessor core. This effectively multiplies the processor's potential performance by the number of cores. Some components, such as bus interface and cache, may be shared between cores. Because the cores are physically very close to each other, they can communicate with each other much faster than separate processors in a multiprocessor system, which improves overall system performance. In 2005, AMD released the first native dual-core processor, the Athon X2. Intel's Pentium D had beaten the X2 to market by a few weeks, but its non-native design of 2 CPU dies and was much less efficient than AMD's native design. As of 2012, dual-core and quad-core processors are widely used in home PCs and laptops while quad, 6, 8, 10, 12, and 16-core processors are common in the professional and enterprise markets with workstations and servers. Sun Microsystems has released the Niagara and Niagara 2 chips, both of which feature an 8-core design. The Niagara 2 supports more threads and operates at 1.6 GHz. High-end Intel Xeon processors that are on the LGA 771, LGA 1336, and LGA 2011 sockets and high-end AMD Opteron processors that are on the C32 and G34 sockets are DP capable, as well as the older Intel Core 2 Extreme QX9775 also used in an older Mac Pro by Apple and the Intel Skulltrail motherboard. AMD's G34 motherboards can support up to 4 CPUs and Intel's LGA 1567 motherboards can support up to 8 CPUs. The modern desktop sockets do not support systems with multiple CPUs, but very few applications outside of the professional market can make good use of more than 4 cores, and both Intel and AMD currently offer fast quad and 6-core desktop CPUs, so this is generally a moot point anyway. AMD also offers the first and currently the only 8-core desktop CPUs with the FX8XXX line. The desktop market has been in a transition towards quad-core CPUs since Intel's Core 2 quads were released and now are quite common, although dual-core CPUs are still more prevalent. This is largely because of people using older or mobile computers, both of which have a much lower chance of having more than 2 cores than newer desktops, and because of how most computer users are not heavy users. AMD offers CPUs with more cores for a given amount of money than similarly priced Intel CPU/Euro, but the AMD cores are somewhat slower, so the two trade blows in different applications depending on how well threaded the programs running are. For example, Intel's cheapest Sandy Bridge quad-core CPUs often cost almost twice as much as AMD's cheapest Athlon 2, Phenom 2, and FX quad-core CPUs, but Intel has dual-core CPUs in the same price ranges as AMD's cheaper quad-core CPUs. In an application that uses 1 or 2 threads, the Intel dual cores outperform AMD's similarly priced quad-core CPU/Euro, and if a program supports 3 or 4 threads, the cheap AMD quad-core CPUs outperform the similarly priced Intel dual-core CPUs. Historically, AMD and Intel have switched places as the company with the fastest CPU several times. Intel currently leads on the desktop side of the computer CPU market, with their Sandy Bridge and Ivy Bridge series. In servers, AMD's new Opterons seem to have superior performance for their price point. This means that AMD are currently more competitive in low to mid-end servers and workstations that more effectively use fewer cores and threads. Risk. In the mid-1980s to early 1990s, a crop of new high-performance reduced instruction set computer microprocessors appeared, influenced by discrete RISC-like CPU designs such as the IBM 801 and others. RISC microprocessors were initially used in special-purpose machines and Unix workstations, but then gained wide acceptance in other roles. In 1986, HP released its first system with a PA RISC CPU. The first commercial RISC microprocessor design was released in 1984 by MIPS Computer Systems, the 32-bit to 2000. In 1987 in the non-Unix Acorn Computers 32-bit, then cashless, ARM2-based Acorn Archimedes, the first commercial success using the ARM architecture, then known as Acorn RISC Machine. First Silicon ARM1 in 1985. The R3000 made the design truly practical, and the R4000 introduced the world's first commercially available 64-bit RISC microprocessor. Competing projects would result in the IBM Power and Sun SPARC architectures. Soon every major vendor was releasing a RISC design, including the AT&T CRISP, 29,000 Armenian drams, Intel i860 and Intel i960, Motorola 88,000, DEC Alpha. In the late 1990s, only two 64-bit RISC architectures were still produced in volume for non-embedded applications, SPARC and Power ISA, but as ARM has become increasingly powerful, in the early 2010s, it became the third RISC architecture in the general computing segment. Market statistics: in 2003, about $44 billion worth of microprocessors were manufactured and sold. Although about half of that money was spent on CPUs used in desktop or laptop personal computers, those count for only about 2% of all CPUs sold. About 55% of all CPUs sold in the world are 8-bit microcontrollers, over 2 billion of which were sold in 1997. In 2002, Less than 10% of all the CPUs sold in the world were 32-bit or more. Of all the 32-bit CPUs sold, about 2% are used in desktop or laptop personal computers. Most microprocessors are used in embedded control applications such as household appliances, automobiles, and computer peripherals. Taken as a whole, the average price for a microprocessor, microcontroller, or DSP is just over $6. About 10 billion CPUs were manufactured in 2008. About 98% of new CPUs produced each year are embedded. See also, Arithmetic Logic Unit, Central Processing Unit, Comparison of CPU Architectures, Computer Architecture, Computer Engineering, CPU Design, Floating Point Unit, Instruction Set, List of instruction sets, List of microprocessors, Microarchitecture, Microcode, Microprocessor Chronology, Notes. References. External links, Patent Problems, Dirk Holt. The CPU Collection. Retrieved December 23, 2009. Gonaji ISHVETS. CPU World. Retrieved December 23, 2009. JAR Copyright Rami Kremet. The Gecko CPU Library. Retrieved December 23, 2009. How Microprocessors Work. Retrieved December 23, 2009. William Blair. IC Die Photography. Retrieved December 23, 2009. John Piko. Great Microprocessors of the Past and Present. Retrieved December 23, 2009. Wade Warner. Great Moments in Microprocessor History. IBM. Retrieved March 7, 2013. Ray M. Holt. The Documents. Wilder Unregistered Trademark S First Microprocessor. Retrieved December 23, 2009. A.